Hi everyone, my name is Isaac Yao, and in today's video, as per assigned by my lecturer, Dr. Peng Mingming, I will be explaining about the uses of ODE, ordinary differential equation, specifically in suspensions. But before that, so let's first talk about the type of ODE that we have learned. So I have my iPad screen here on screen, showing you that here are all the types of ODEs that I have learned so far. So as you can see here, we have first order and second order. Let's start with going through the first order ODE. So the first order, a simple one like this, is where we can do the separation method, bringing the x on one side and y on one side, and we can separating them by integrating them on each side. Next one, to test the degree of n, to see whether it's homogeneous ODE or not, we introduce this. For example, this question, we introduce lambda, and then once we solve it, we'll see is it homogeneous or not together with the function. So in this case, we have a homogeneous equation with a function of 2 because of the power. And next one, to test the exactness of ODE, to see whether it's exact or not in this form. So we test the exactness together with lambda again, once again. And then if it's not exact, we can make it exact again by introducing functions like this, fx, so that we can take out or extract out the fx from there later on to times back the value of fx into equation to make it exact. And then next one, to see whether it's a linear ODE or not. This is the form. We have the y prime here, or dy dx together with px and rx, and we have the r unknown over here. So here is an example, and making sure that y prime, the front of y prime is 1. So this is when you solve with the help of Bernoulli equation. The main part is when you have a linear ODE, but then we have y in this case. So y to the power of a, we solve it with this form, and then with this equation we can solve it later on. So now the second part, the second order ODE, is when you have prime or differentiate by 2 times. So it is actually in a quadratic form, which you can solve with the help of the quadratic roots equation and finding the roots later on, which we have the auxiliary equation, finding roots to tell us which case it is. We have case 1, 2, and 3 as shown here to see which case it is, and then we will choose which equation to use later on to solve. And then this, lastly, is a complicated one where we have to find yp and yh. We have yh if our second order ODE does not have 0 over here. Instead, we have another value over here. We can solve it to get yh. So these are all the ODEs that I've learned so far. Okay, so now for the next part, I'll be explaining how to derive the ODE equation for the suspension. As you can see here, for the suspension shown on my screen right here in the car, we have the suspension holding the mass of the car and also the mass of the wheel plus the driving system. So in the suspension, we have the damping part and the spring part. So we have two constants, which are the damping constant and also the spring constant. Mass 1, I denote mass 1 as the mass of the car, mass 2 as the mass of the driving system. So we have all these forces acting to balance out the equations acting on mass 1 and mass 2. So as you can see here, this is the equation for the spring. K is the spring constant, and y1 minus y2 is the extension of the spring, or the difference in the distance traveled. Because of y2 and y1, I denote it as the distance by the mass 1 for y1 and mass 2 for y2. So as you can see here, this is the same, but then we have negative k because of the force acting downwards. Same thing here. But then for the distance, for y1 and y2, I put prime, which means I need to differentiate one time, because this is the damping system, or the damping part, in which the damping constant is denoted by c. That is why we need to differentiate once. For this part, this is where the mass of the driving system and the mass of the car is acting on the wheels. So air pressure is taken into consideration. So I take this as the constant of the wheel, and instead of y2 minus y1, I use y2 minus r as the radius of the wheel. So these are the spring constant and the damping constant. With the help of all these forces, I can later on derive the equation for equation 1. This is for the top of the spring, and 2 for the bottom of the spring. But then we can't use the bottom of the spring here for our equation, for our modeling question for the suspension, because the air pressure on the wheel is taken into consideration. As shown here, we have this extra value here with the distance of r. I take it as the radius, and the constant, which is the constant of the wheel, or the air pressure in the wheel. So we have two of these equations, but mainly we'll use this to solve modeling question for suspension. So let's move on to the modeling question for our suspension system. So okay, I have this question on the modeling question shown in front here on my screen. So you can also see on my iPad screen, I have all of this data that I've extracted out from the modeling question. So let me read out. The modeling question shows that a car body has the mass of 1500 kg. So I denote mass 1 as mass of car, 1500 kg, and it is connected to a driving system consisting of all the stuff which weighs 130 kilograms for M2. And then the single suspension unit consists of spring constant and also damping constant as such, K and C, shown here, 300 kilograms per second square and 300 kilograms per second. So determine the equation of motion of the suspension unit. So we have to create an ODE equation, a full equation, to state that a condition with the change of time, what will be my velocity, what will be my distance. So here I have condition A and condition B as shown here. A is suspension has an extension of negative 0.3 meters because it's compressed when time is 0, and the velocity experience is 1.5 meter per second when time is at the 5th second. So from our equation earlier, that is this equation, we have gotten a lot of y1 minus y2. It's just that we have the prime and the double prime. So we let y1 minus y2 as z, which is our distance. Okay, so after creating, substituting z into the equation, we will get this equation, and we will have m1, c, and k in from our data. So let's write out the equation first. Okay, so as you can see, this is the equation after substituting all the values for k, c, and also m1. So let's write out the auxiliary equation. Okay, so this is our auxiliary equation as shown here. So to substitute lambda into the equation, and then now we can find the roots, see whether it's case 1, case 2, or case 3. Okay, so as you can see here, I have lambda given both of these roots. We have plus and minus. So with the imaginary root, we know that this is case 3. And case 3 states that it is overdamped. So overdamped means the stiffness of the spring is way too stiff, so that the suspension experiences even with high amount of forces, suspension is still very stiff. So let's write out the general solution for this case 3. Okay, so as you can see here, I've written out the formula for this z in terms of t, and also I differentiate it one time so that I have both of these equations, which I can sub the initial conditions as shown in my A and also B with my time 0 and 5 for both the equations, and also negative 0.3 and 1.5 as the distance and the velocity to help me find the value of C1 and C2. So let's calculate that. So I have gotten my value for C2 as 5.58 and C1 as negative 0.3 after substituting the distance as negative 0.3 and the velocity as 1.5. I will get both my C1 and C2, which I can then substitute back into this equation. So let me do that. Okay, so as you can see here, after calculating and after substituting the value of C1 and C2, this is my main equation. And you know that in my equation, this is a second order homogeneous linear ODE as shown here. So, and because it's 0 on this side, and then we don't need to calculate YH, we only need to calculate YP as shown here. And this is my equation.